Acceptance sampling is a method used to accept or reject product based on a random sample of the product. The purpose of acceptance sampling is to make a determination about lots or batches of a product, accept this batch or reject it, rather than to estimate the quality of an entire lot. Acceptance sampling is especially useful when buying large batches of a product. In these cases, it may be too expensive or too time-consuming to test every single item in the batch. Acceptance sampling involves the multiplication rule of basic probability because we're interested in the probability that item 1 and item 2 and item 3, for example, of our sample have no defects. So say we select 3 or 4 items from the batch, and we'll accept it if they're all good. So the probability of item 1 being good, and 2 being good, and 3 being good, and 4 being good, for example. So there's that word "and" that tells us this is the multiplication rule. So let's look at an example that uses acceptance sampling. Okay. A sporting goods company imports fleece jackets from a foreign supplier. Upon delivery, a sample of the jackets is randomly selected without replacement. Okay, we're seeing some key words here, without replacement, for inspection, and the entire shipment is accepted only if every item in the sample passes inspection. Okay? So, in a shipment of 450 jackets, 18 will be defective from this supplier. A defective jacket means that it might have a non-working zipper or loose stitching. These are examples of defects that might turn up when inspecting the jackets. If 3 jackets are randomly selected for inspection, and recall this is without replacement, you wouldn't want to inspect a jacket, throw it back in the pile, pull another one back out. You might pull the same jacket again. So obviously without replacement. If 3 jackets are randomly selected without replacement for inspection, what is the probability that the entire shipment will be accepted? So let's look at what we know so far. We know this is without replacement. And so what does that mean to us? Well, that means that these are dependent events. And so what does that mean? Well, that means when we use the multiplication rule, the probability of A and B is computed by saying, well, that's the probability of A times the probability of B, given that A has already occurred. Okay, so the probability that the first jacket has no defects times the probability the second jacket has no defects, given that you've already pulled one jacket out of the pile to inspect. But recall we learned that there are times when it's acceptable to treat dependent events as independent events, but it has to meet, our situation has to meet a certain criteria. So let's look at the numbers that we have here. We know that we're going to select a sample of 3, and our population size is 450. So the rules said that you have to answer the question, is N less than or equal to 0.05 or 5% of the population size? Is your sample size less than or equal to 5% of your population size? Okay, let's see if we meet that condition. Let's plug in what we know. 3 less than or equal to 0.05 times 450. That's the question. Is this a true statement? 3 less than or equal to, well, 0.05 times 450 is 22.5. So, yes, 3 is less than 22.5, so we may treat dependent events as independent events. So I think I mentioned before that this is not going to be, you're not going to be told, okay, this meets the qualification, this problem meets the requirements. You are going to have to read the problem and determine whether or not you can treat these dependent events as independent events by doing this little analysis. That's going to be expected that you would do that. Okay, so if that's the case, then now our calculation changes to a with replacement situation where we will calculate the probability of A and B as the probability of A times the probability of B, because there's no condition. We're treating them as though they are independent events. Alright, that decision's been made, and what we know now is this is going to be an easier calculation because we don't have to worry about conditional probability. Alright, so we want to know what's the probability if we select 3 jackets and inspect them. What is the probability that the entire shipment will be accepted? Well, the problem statement said the requirement for acceptance only if every item in the sample passes inspection. So in other words, all 3 jackets must pass inspection, must have no defects. That's our case for acceptance. So we need to know, well, what's the probability of a defect? So the probability any one jacket has a defect, you pull out that first jacket, what's the probability it's defective? Well, they told us that there are 18 defective jackets in a shipment of 450 total jackets. So the probability that any one jacket in that shipment is defective is 18 divided by 450, which is 0.04. Okay. Well, the probability then of no defect, that you reach in, you pull out a jacket, it's not defective, is easily computed because that'd be 1 minus the probability of a defect, because those are our only 2 choices, right? That's F. Either a jacket is defective or it's not defective. So these are complementary events, and so defect would be the complement of no defect. Okay, so 1 minus 0.04 is 0.96. There's a 0.96 probability that one of the randomly selected jackets has no defect. Alright, well, the probability that we accept this shipment, probability accept shipment, that's the question. What's the probability that the entire shipment is accepted? Well, that's only going to happen, that's the same thing as, and it will only happen is if we get no defect for the first jacket. I'll use a little subscript 1, first jacket, and no defect for the second, and, see if I can squeeze this in here, no defect, I'm going to abbreviate, for the third. Okay? First one, no defect, and second one, no defect, and third one, no defect. Multiplication rule, and. Okay? Well, the probability that the first jacket is not defective, we said no defect is 0.96. And because we're treating these as independent events, then the probability that the second one is not defective would be 0.96. Obviously, we would be putting that jacket aside before we pull another one out, but because we met the conditions that our sample size was less than or equal to 5% of our population size, we can treat these as independent events, so we do not have to factor in the fact that we've put that first jacket aside. Okay? Times, now the third jacket is selected, the probability that it has no defect is 0.96. So again, we see that we could write this much more simply, is 0.96 to the third power, and that result is 0.888 0.73736, carrying it out several decimal places, or approximately 0.885. Say we want to round to 3 decimal places. So we could state in conclusion that there is an 88.5% chance the shipment will be accepted. Okay, so this is acceptance sampling.